All right. Let's work through this first one, and then I'll give you a little bit of time to look at the second one. And also, I am going to be arguing with the iPad all day, just so we're aware. So I may or may not be able to go back to pages throughout the day, just so we're clear. So I'm going to always like stop and check and make sure we don't need more time on stuff. So when we're working with quadratic formula, what we need to know is we need to know what's our A, we need to know our B, and we need to know our C. What is our A for this first one? 1. What is our B? -9. Good. And what is our C? -20. Hey, guys, there's classes going on and I can hear you through the wall. Thank you. Okay, so first thing we're going to do is we're going to do this discriminant. That's going to be the easy way to go. If we do this bit first, it's a little bit easier for us. So the very first piece we want to do is that b squared minus 4ac. So I'm going to have my -9 squared minus 4 times our a, which is 1, times our c, which is -20. We're going to simplify that bit first. What do we get when we simplify just the discriminant? Yes, we get 161. So that means we know we're going to have 2 real roots. They might be decimally, but we're going to have 2 real roots when our discriminant's positive. So to get our full actual answer, that's when we're going to take that into our full formula again. We're going to have our opposite of our b, -9, plus or minus the square root of our discriminant, that 161. And that's all going to be over our 2 times our a, which is 1. And we're going to try and simplify that as much as we can. So our solution here, there's not a whole lot we can do to simplify it. The opposite of -9 is going to be a +9. And then we have our plus or minus. The square root of 161, we put that in the calculator, our yellow calculators that are the super duper awesome best friends that'll simplify radicals for us. Can't simplify it. There's not any perfect squares that are factors of 161. I could get it to be a decimal, but that doesn't really help me, especially when it says we want this in simplified radical form, which means we're still going to have a radical. We are going to have our denominator, though, of a +2. So this is our first one, solving the whole thing, quadratic formula. Now you can use that kind of as a guide for that second one. Give that second one a shot. See what we can do there. And we're going to do this one pretty much the exact same way. We're going to start by finding our A, B, and C. What do we get for our A? 2. What about for our B? -5. And our C? Gorgeous. We're going to, again, start with that discriminant, starting with the guy that's under the square root. So we're going to have our b squared minus 4 times our a times our c. And we can type that statement into the calculator. As long as you put it in with the parentheses, you can rock and roll in the calculator with it. -5, parentheses, squared, minus 4 times 2 times 7. What do we get? -31. So what kind of roots are we going to have here? When our discriminant is negative, we get imaginary roots. So what that looks like when we substitute this into our quadratic formula to get our full answer, and the reason that happens, when we substitute this in and we have our opposite of b, -5, plus or minus the square root of our discriminant, that's our -31. And since this is the piece that goes inside the radical, that's why this being negative gives us imaginaries. Because now we have the square root of -31. And it's over 2 times our a, which is 2. So we can do this substitution, and then we can simplify it a little. Just a little, though. Because 31 also doesn't have any perfect squares as factors, so we can't do a ton of simplifying here, but we can do a little bit. Because my opposite of -5 is a +5. And then we know whenever we have a negative number under a radical, I can take that negative sign out by instead writing an I. So I can put this as I square root of 31. Square root of 31 will not simplify any further, but I can write it like that. And that's going to have a 4 in the denominator. So this is our simplified radical form answer. There we go. Sorry. Questions on that one? I think I have a way to get it back, but I'm trying to figure out a way to do screenshots. My screen's in a mood. Okay. So we're going to look at our very last concept in this chapter. We're going to do it today and tomorrow. We're going to look at page 18 at the bottom, and we're going to get all the way to the bottom of page 19, and then tomorrow we'll do page 20, and that's the last page. So that's kind of the plan. But this does require us to remember something from last chapter. Oh, snap. I know. Horrifying. We've talked about a system of equations before. Remember what a system of equations is? We did these actually a bunch last chapter. And what a system of equations is when we have more than one equation that we're solving at the same time, or solving together. So like technically the way we'd word this would be a collection of more than one equation that are solved together. We had these with 2 variables. We had these with 3 variables. We had all kinds of pieces with it. But like an example of a system of equations, it'd be like 2x plus y equals 7 and y equals 3x minus 4. Like this is a system of equations when we have 2 lines. We did it with our, 2x plus 3y plus z equals 4 and 3x plus 4y plus z equals 7 and those guys. Those were also a system of equations. So anytime we have more than one equation that we're working together, it's a system. Where are the solutions when we're looking at a system? For example, if we looked at these two lines, you get one line that goes like this, and one line that goes like this. Where would the solution to the system be if we did our graphing? Where they intersect. It's the point where they cross. The solution to a system is where the lines intersect. At a point. So our system comes in the form x comma y. Our solution is x comma y. So we need our point, our ordered pair. When we were working with our lines, we always got a point where they crossed, or we'd have our two parallel lines, or our infinitely many solutions, which is when we have infinite number solutions. Parallel lines, we had no solution. What we're going to do today is we're going to be looking at systems of equations, but one of our equations is going to be one of our quadratic guys, one of our x squareds. So at least one of the pieces of our system is not a line. So what this is called is a nonlinear system, because one of our equations is not a line. So again, I'm never going to ask you to like regurgitate out the definition. You don't have to like memorize them, but a system of equation just means we have more than one equation and we smush together. So we're going to start by kind of talking about our options for solutions, and then we're going to solve two systems together today. Does anyone need more time on this page? Since I can't guarantee how easy I can get back. Okay. All right. So bottom of page 18, we have this picture here. So here we have a parabola and we have a line. How many times do they intersect? This parabola and this line? Not where, just how many times? I was going to say, I know we spotted this one because we started calling out those numbers. So one here and one here. So we have not one, but 2 points of intersection. So these two equations intersect at 2 points, which means this system has two solutions. I could try and find these addresses. I could try and find these numbers. This one's like -1.5, 2 1/4-ish. We're not going to go there if it's decimally on a graph. If it's on a nice tidy intersection, we can find it. But if it's decimally and gross, we're for the most part going to be solving these another way. This is just a visual. So our solutions happen where our lines cross. So we can have two solutions. We have two more examples on the next page. It's just split across a couple of pages. At the top of page 19, we get this picture. How many times do our line and our parabola cross here? One time. So I only have one place where they cross. This line just comes in and kisses our parabola. It just goes and goes past. So it's only intersecting at 1 point, which means this system only has one solution, has a single point. I could find my x and y. This one, it actually does come at a nice tidy intersection. It's got that little black point on it. So this solution would have a system at 4, -5. That's this point where both lines are true, both lines cross. We could also have in a system that looks like this. What do we notice about the intersections here? They don't touch. Do not intersect. The functions do not intersect. That means there is no solution. So we can have two solutions, we can have one solution, we can have no solutions. All of those are possible options. So when we're working with systems, especially systems that are not lines, we have a couple of different ways we can approach it. But we may get no solution, we might get one solution, we might get two solutions. And so we're going to do our first system ourselves by graphing, which is not going to be a super common way that we solve them because it really only works in very specific circumstances, but we can do it. Take that. So let's look at this one. This is our example 2 in the middle of the page. We're given our equation here of 4x minus y equals 6. And then we have this y equals minus 2, x minus 2 squared, plus 2. So this guy's a line. Great. This guy, not a line. This guy is a parabola. This is how we actually started this chapter. On page 2 in our packet is when we started actually graphing these. We graphed this one like this. Actually, the bottom of page 3 is when we graphed one like this. And all of page 4. So this equation, I'm going to start by graphing my parabola simply because it's easier to do sometimes with the blank page to do the more complicated guy. And then we can graph our line afterwards. So I'm going to start by graphing this piece. It's in our transformation form. Again, if you need help with that, look at pages 3 and 4 is where we were doing this. And that's when we would find our A, H, and K. What is our A on this one? -2. So we know when our A is negative, we're going to have an upside down or a frowny face parabola. What is our H on this one? +2. This is the one that if we think through that original formula, which again, this original formula will also be on the test. We just need to know how to use it. As soon as I can get a color that I want. Our y equals a x minus h squared plus k. That formula will be there. You just need to know how to use it. So what's our k? Careful, careful. So h is always going to have the opposite side of the expression, but k does not change. So k is still going to be +2. So this guy will always have the opposite sign of the expression. If it's inside the parentheses, our answer has the opposite sign. K is just tucked on the end. He doesn't have to be changed to be weird. So make sure we're practicing that. It's a good chance to review some of those things. What that tells us is when we're looking to fill in our table for this quadratic to find our points so we can find x's to make y's to plot up, in the center goes our HK. H with the x's, K with the y's. So our vertex, our HK, is going to happen at 2, 2. I know where my vertex is. It's right here. To get more points to plot this up, we have lots of options on how to fill this table in. I'm just going to rewrite that too. But honestly, the easiest way to kind of go is usually to just find a couple of numbers bigger. So maybe grab 3 and 4. A couple numbers smaller, maybe 1 and 0. And substitute those into our equation. There's other ways to do it. Absolutely. But I could just take these numbers and put them in for x. So I can have my -2 substitute in 0, -2 squared. And you can type from the calculator. The whole thing. I put it on the calculator, but my computer's in a very severe mood, so it won't let me pull it up without being under the words I've already written. I think. Let's see. Yeah, it's under the words I've already written. So you can type things into the calculator like this. That makes the screen really small. But I can just straight up take my equation and substitute in values. I've substituted in the 0 right here. Just straight up into my equation that we have right here. I type the whole thing in, just substituting in the 0, and we get -6. So I know for 0, we get -6. I could do the same thing for that -2. Let me do it. So my -2, 1 minus 2, close the parentheses, n squared, plus 2. Just type the whole equation in and let the calculator do the work. And then we know if we set that up right when we do the very next one, and I switch that 1 out for a 3, for my -2, 3 minus 2 plus 2, we get exactly 0, which means we know for a fact we got our vertex right, and the bottom one we don't have to fill in because we know it's going to match. Because if these two match, these two are going to match. So that gives us all our values. You can use our calculators for it, so we just need to be careful. And that gives us a bunch of points we can plot up. I know we're going to have a point at 1, 0, and we're going to have a point at 0, -6, and we're going to have a point at 3, 0, and at 4, -6. So our graph is going to look like this for our parabola. That gives us one of our pieces. It's been a hot minute since we graphed a parabola. Questions on that bit? Okay, the other thing we need to do is we need to graph our line. So we are given this 4x minus y equals 6. I'm going to write it over here. And we want to graph this. So that means I could graph it as it is. Just find like x, y intercepts and go from there. I could solve this into slope-intercept form. Usually we're a little bit more comfortable with that. But we can graph this line however we need to. If we want to get this into slope-intercept form to make this be easier, what do we need to do? How could I make this have y all by itself on one side?
The x to the other side.
Yeah, we can move the x to the other side. I can minus 4x from this side, and I can minus 4x from this side. That's going to give us that minus y equals minus 4x plus 6. I don't like that being that skinny. I'll go back to 4. And we're almost there. What do I need to do? Divide by -1. Divide by -1 to absolutely everybody. That's going to give us that our y equals 4x minus 6. So again, you don't have to do this to be able to graph it. There's lots of ways to do this. Probably the putting it into slope-intercept form is going to be the easiest option. How do I graph that line though? Where do I start? This is our y equals mx plus b. Where are we going to start? This is my first point.
-6.
-6. My y-intercept at -6. How do I find my next point for my line? We're going to move with our 4/1. So we're going to go up, 1, 2, 3, 4, right, 1. Up, 1, 2, 3, 4, right, 1. Up, 1, 2, 3, 4, right, 1. The more points we have, the easier it is to connect them up. We would like to use a ruler to do so. I think in this particular form, I do not get to have a straight edge tool. Yay, fun times. You should use a straight edge. My iPad is a jerk, so I don't get to use one. It's gonna be kind of like that. we're going to need to be really careful, and we can look at the points that we made, because where do they cross? Where do we have intersections between our line and our parabola? Ignore the fact that my parabola is slightly wonky. My line is also slightly wonky. Where did we have, for both of them, a dot that we drew in the exact same spot? Yes, so on our -6 intercept, so just be really careful if we have those numbers switched. So our x is 0, our y is -6. So one of our solutions is happening right here at 0, -6. Where else do we have a solution? At 2, 2, up here. At that vertex right where they're crossing. So 2, 2 is another solution. We wound up with two possible solutions, or two solutions on this one. So remember, we can get one solution, we can get two solutions, or we can get no solutions. So if it's hitting in two spots, which, yeah, this one's gross, but it is hitting in two spots, we get two solutions. We will not get more than two solutions when we have a quadratic. Not going to happen. Questions on this one? This is probably the most annoying way to do this. Workable, absolutely functions. We can totally do this as long as we remember how to graph parabolas, which we need to remember for the test anyway. So it's a great way to review. Snap. But what we're going to do more frequently to solve these is solve them algebraically. So just like we did when we were solving our systems and we took one equation and we smashed it into the other equation because we knew something that like x equaled or y equaled, we can do that here as well, as long as I have an x equals or a y equals. Here we have our y equals x squared plus 2x plus 7, totally fine. We also have 6x minus y equals -3. We want to be able to solve this with substitution. Now I absolutely could. Right here goes, sweet, I have a y equals and substitute it in. But I really don't want to have to deal with a minus and all of this, you gross. So what I'm going to do is I'm going to take this equation here and I'm going to switch it into slope-intercept form so that I can just like not have to substitute something into a -x. So you don't have to do this, but it is generally kind of much easier if I have y equals and y equals. Not required, but it is easier if we do not have to substitute in when it's a minus sign, so I don't have to distribute stuff because ew. So I'm going to rework this guy so that I can have a y equals and I don't have to have a minus y because ew gross. So what I'm going to do for that is I'm actually going to add y to both sides of this equation so that I'm going to have my 6x equals y minus 3. And then since I want that y by itself, I'm going to go ahead and add 3 to both sides. And that's going to give me my 6x plus 3 equals y. Now again, that's not something we have to do, but it is genuinely a bit easier if we do. Because now I know that y equals this thing right here. So what I'm going to do is I'm going to take this in all the way up to my other equation up here, and I'm going to substitute that in place of the letter y. So I'm going to do this as a substitution and put my 6x plus 3 and set that equal to my x squared plus 2x plus 7. And so I'm substituting that equals y in place of the y. And now this looks like a mess, but if we ignore everything else that it came from, this is our regular solving stuff. So we can solve this in any number of ways. I could make it equal 0 and factor. I could make it equal 0 and do the quadratic formula. I could make it equal 0 and graph it. It'd be a wild choice, but it's doable. I could set this up with my x's on one side, constants on the other, and complete the square. That is hard. So I have a lot of options when it comes to solving this. Probably the easiest way to go is going to be to try and factor it. So what I want to do is I want to get this equal to 0 so we can see if this will factor. So we're going to substitute something in so we smush our equations together, and then we're going to try and get it equal to 0. So what that means is I'm going to need to come through here, and I need to minus my 6x from this side, which means I'm going to minus 6x from this side. That's going to give me our 3 equals x squared minus 4x plus 7. I still want to try and get this thing down to 0. So I also need to minus 3 from both sides. That's going to get us to our 0 equals x squared minus 4x plus 4. So by substituting these together and setting it equal to 0, we just get a different quadratic. But we want to solve this now that we've got this set equal to 0. I could factor it, I could put it through the quadratic formula, I could try and complete the square. Bold strategy, but it works, like totally fine, you can do it. Probably the easiest option, unless you are super comfortable with quadratic formula, is going to be to try and factor this thing. So that's the way I'm going to go. If you want to go a different way, it's totally fine. There's lots of pathways through it. I'm going to try and factor this, though, especially since we do not have an a value of anything other than 1. So I can take the shortcut when we factor. This is when we put our a times c at the top. 1 times 4 is 4. B goes at the bottom, negative 4. Do we know a pair of numbers that's going to multiply to make a positive 4 and add to make a negative 4? I heard it. Our negative 2 and negative 2. Negative 2 times negative 2 gives us a positive 4. Negative 2 plus negative 2 gives us negative 4. Whenever we have the exact same number on either side, that means we are looking at our perfect square trinomial here. So we could put this in perfect square form, or we can put it in factored form. Either way. You can put it through the accent box, you can put it through split the middle, you can put it through any kind of factoring that you'd want to, or we can take our shortcut, since my a value is 1, where I know it's going to be x with that minus 2, and x with the other minus 2. You could also write that as your x minus 2 squared. Totally valid. So we've gone from these two equations down to one equation, down to one single factored form, but we're trying to get down to an x equals. We did these on page, I want to say 10. Is where we had these? Yeah, solving by factoring. We have on page 10, so if you need to look back, that was a good place to look. How do I get to an x equals on this? How do I find a solution? You could also write this, I know some people are going to see this area, r x minus 2 squared, and you could solve it with square roots this way. Absolutely valid. When we are in factored form and we're trying to find our root solutions, zeros, x-intercepts, that's when we come through and we set our factor, our x minus 2, equal to 0. And we do that with every factor that we have. X minus 2 equals 0. Well, if I add 2 to both sides, what we get here is our x equals a positive 2. And in fact, we get that over here as well. Whoops, that was not what I meant. There we go. Laser pointer. Over here as well. Because these are the exact same factors, so we're only getting one single x. We got it from our green factor and from this pink factor. So we're only going to have one solution here. Is my solution to this system x equals 0? it is not. Because remember, our solutions are the point where they cross. I know the x. I do not know the y right now. How could I find the y? Plug it into one of my equations. I mean, I could use this one. More power to you. I also know this guy's a y equals. I can substitute that 2 in over here. 6 times 2 plus 3 to get y. Y equals 6x plus 3. So that means our 6 times that x of 2 plus 3 equals our y. Substituting that 2 in for our x. So what is our y? What is 6 times 2 plus 3? 15. So 15 is our y. So our solution is the point 2, 15. We only have one solution in this case. Whenever we have the exact same factors when it's set equal to 0, we're going to get one solution. If it's going to look like this, we have our perfect square equal to 0, we're going to get one solution. If we have two different factors, we're going to have two different solutions right there. So we can get one solution, we can get two solutions, we could get no solutions, which just means everything would cancel out. We are going to do 2 more of these tomorrow. This is our last bit in this chapter. Since this is our last bit in this chapter, and what I have right here is the last homework of our chapter. So I'm going to pass this out. We're going to practice 2 more of these tomorrow. The page 20, we're going to do those 2 tomorrow, and then we'll have time to work on this. I will also get the chapter review printed out for tomorrow. Wednesday, we'll have the whole time to review and ask questions. Thursday is PSAT day. Friday's a chapter test. That's kind of the plan for the week. So I'm going to pass these out. It's the last homework of the chapter. And again, we're going to work through more of these tomorrow. I'm so good. Capture screen. There we go.